I guess I'll get started.
Yep.
Can everyone hear me okay? All right. This has nothing to do with my presentation. Does anyone know where that is? Does it look familiar?
China.
Nope. It's not in the U.S. So this is Mizenhead, which is the most southern point of Ireland. And for many years, they operated a radio beacon, medium and high frequency wave beacons off this rocky Irish coast, basically for the shipping industry. And they would home in on the beacons, but it would warn them that they were approaching the shore. The radios are decommissioned now. I was there last May, and it's a pretty amazing site to visit. I have other photos. Maybe that's another presentation someday. But if you're ever over there, it's definitely, it's out in the middle of nowhere, but it's definitely worth the trip. So.
How do the ships know now that they're approaching land since the beacons are turned off?
Well, now they use GPS, and the navigation is much more accurate now, so they really don't have to rely on that. But they had light beacons, radio beacons, and all that. There's a lot of shipwrecks off because the shore is very uneven and jagged, and it's like that through a lot of the southern and southwestern part of the country. So there's a lot of shipwrecks laying there, and so you probably can't see it. There's a couple old towers still up. A lot of it's been taken down now. But they had a lot of stuff there. And of course, this photo does it no justice at all. This is hundreds of feet high, these cliffs. You can see there's a little footbridge down there. It goes out of sight, and way up by that building, there's a parking lot where you can park. You walk out here, this peninsula continues out, and the station is right on the end of the peninsula. So, what's that? Mizenhead, yes, Mizen, M-I-Z-Z-E-N. So let me get my act together here. About a year ago, I did a presentation on an antenna I use at my house. It's basically a doublet. I think a lot of you were here for that. I don't know if how many of you ever tried that or whatever. But today, Bob mentioned I use the EZNEC antenna analysis software to help design these things. I'm not going to go into a lot of detail about using that program today. I'll jump in and out of it once or twice, that's it. I mainly use it to develop the azimuth and elevation plots that you're going to see here today. The basic topic here, I like to pick an antenna and show how I use the software to get there. So this is called a Vee Beam. Has anyone ever used a Vee Beam? No. Oh, Bob, oh, you have too. There's two.
That was our primary antenna in Antarctica.
Oh, really?
For the station I was at, yeah.
Well, in Antarctica, you had a fair amount of space to deploy it, didn't you? That's why there's not many around, because they take up a lot of real estate. But anyway, so we'll talk about the Vee Beam a little bit today and variations on that theme. I'm going to talk about how it's generally used and how we might also use it in a smaller portable configuration, either for emergency communications or field day or some reason like that where we have to go out in the field and set something up that's relatively easy. As you can see, there's not a lot to it. If you took these ends and pulled them straight, it's basically a dipole or a doublet. And all you do is take, instead of having it in a single axis, you just go like that. Pretty simple. So it's not that much harder to set up. So anyway, when we're setting up home stations, of course, the holy grail, I guess, antenna-wise, is to have a nice Yagi with a rotor and a tower and all that. And those are nice when you can have them. I think all of us have probably used Yagis or Yagis, as it's supposedly pronounced. But there's a bunch of reasons why it may not be practical for our home installation. And certainly around here, the HOAs, municipal ordinances, county regulations may prohibit that. They're quite expensive, an option, probably the most expensive type of antenna option. And maybe you just want one all-band antenna that you can put up and you can use it across all the frequencies from maybe even 160 or at least 80 meters up to 10 meters through the HF spectrum. And maybe you have the room for a wire option. So that's what we're going to explore a little bit today. On a portable arrangement, what we've been doing at this field day event that Bob Clark was telling you about earlier, we put tower sections together, we build this Yagi antenna, and we pull it up in the air, and it's a bunch of people and this and that, and it's quite a project. And sometimes it comes out right, and sometimes it doesn't. And so it is cumbersome, it's time consuming, and as time goes on, there's fewer and fewer of us at a field day, and the ones that are there aren't any younger than they used to be. It's nice to look at what other options might be available other than putting the Yagi and the tower up in the air. And of course, if you drop it, this kind of shocked me. So I was on the M Squared website the other day. It's $3,400 for a new KT-34. That's pretty serious. So anyway, and if you put one up, you still need another antenna for the low band anyway, right? So most wire antennas don't provide nearly as good a performance as a Yagi, but the Vee Beam is maybe an exception to that. One option, of course, I used this slide last year. One option is to just stick a bunch of antennas on a truck, go to the top of Loveland Pass, and operate from there. But I don't recommend it as a long-term solution. So this was K0EU and I, we were operating the Colorado QSO party as a rover. So we did 18 counties in a day between 6 a.m. We started in Phil's driveway, worked him on 9 bands, and took off from there. And we went all the way to Craig, through Steamboat, down through Moffett County, down through Summit County, over Loveland Pass, and then up, what do they call that? Peak to Peak Highway up north of, west of Boulder, and all the way back down the Front Range. So it was a long day. So what's this Vee Beam thing? So basically, unlike a dipole, the legs are generally longer. This is how we develop some gain with it. So these are really 2 end-fed long wires fed with a balanced feed line. And what we do is, usually you try to get them to be 2 wavelengths or more in length at the lowest frequency we want to operate. That's the way to get the best performance out of them. And this is another one of those things where the longer the wire, the better, generally, the more gain you'll get. And it's also, if any of you have heard of a rhombic antenna, this is a half of a rhombic. So a rhombic would continue on here to a point and then back here and make a diamond shape. And it basically doubles the gain of this configuration. So, or like I said, it's like a doublet, and you just fold the legs this way. So the advantages of the Vee Beam is that it's wire-based and lightweight. It's cheap, way cheaper than a KT-34. You don't necessarily need towers to hold it up. You can use a rigid mast, Rowan push-up mat, a chunk of pipe, irrigation pipe, whatever. You can put together inexpensive masts with 2x4s. It'll basically cover all the bands across the HF spectrum. As you go higher in frequency, the performance improves. But it's one antenna for everything, really. And at the higher frequencies, you can get useful gains. And I'd say from a tri-bander to the equivalent of a 5-element Yagi in certain directions. So if you make the legs long, you can really get some good gain out of it. I've read you can stack them vertically. I've never seen that, but you could do that and get another 3 dB of gain on top of what you built the first time. The other nice thing about it is most antennas, when they're low to the ground, the radiation angle is very high. And you really have to get them in the air. A Yagi for 20 and up really should be, 70 feet in the air ideally. And this provides comparative low angle radiation at a much lower height. So you don't need the height that you would with the other antenna.
So you're using the ribbon cable for the...
Yeah, you can make your own balanced feed line, or you can use the 450 ohm ladder line, 300 ohm ribbon. If you're running less than, say, a few hundred watts or less, you can use 450 ohm line or 300 ribbon. But if you're going to run 6, 7, upwards of a kilowatt, you want to make your own 600 ohm feeder and space the wires about 6 inches apart. So.
That feeder is an integral part of the antenna.
What's that?
Is that an integral part of the antenna?
Yes, yes, yep.
So how high does that have to be? How long?
Well, you have a lot of flexibility in how long it is. In my other presentation I did last year, there's certain lengths you want to avoid because they're resonant on certain bands and hard to tune. But outside of those limits, then you have quite a bit of flexibility. The thing about the Vee Beam too is it's bidirectional. There's a little bit of directionality in the direction of the beam, but it's only a dB or two. So they're essentially bidirectional. You can make them unidirectional with terminating resistors at the far end. But what that does is absorb the back reflection, and it cuts the gain down. So, it's kind of self-defeating in some ways. But for point-to-point HF communications, like when you're in Antarctica, right? I mean, you're trying to get to a certain area, you can just put a big Vee Beam out there and, it'll go both directions. So, and you'll see that in the plots here. The other thing about it is you get multiple side lobes, so you don't have to put a bunch of Vee Beams around all over the place. So you do get side lobe radiation that's useful versus a Yagi that's unidirectional. Now there's downsides, of course. You need quite a bit of space. Like I said, they are bidirectional. If you're looking for front to back ratio, this isn't a good way to go. The main radiation lobe is fairly narrow compared to a Yagi. I'll show you that graphically here in a little bit. And you need 3 supports. So a dipole you can have 2, right? But as soon as you bend it, you need 3. So, and you need the balanced feed line and a good tuner to match it to your radio. The smaller versions don't have any gain on the lower bands, but then again, a tri-bander doesn't either. So, but that's one of the things to keep in mind. So we'll talk about characteristics of long wires. Over here we have, a half wave, which would be a dipole. And remember, everyone should know this, that wavelength is 984 divided by the frequency in megahertz, right? So for 20 meters, it's around 70 feet-ish. So you have this radiation pattern. Hopefully you can see this okay. It's basically perpendicular to the wire. Can you guys see that pink shading? Okay. And then as the wire gets longer, things start to happen where the lobe of transmission starts to split and move relative to the axis of the wire. So as we get to a 1 wavelength wire, then we get these 4 lobes start to go in different directions. And we get to 3 half waves or a wave and a half. Then you get the 4 change direction again. And they also get stronger. So in general, what happens on any long wire is that the longer they are relative to the frequency they're used on, the primary lobes get stronger, they get narrower, and they get closer to the axis of the wire. And the other thing that happens is you start to see more and more of these side lobes that start popping up in the middle. That's, in a nutshell, how these work. Does that make sense to everyone? Okay. So this is an eye chart. I won't go all over it. But this tells you that as your wire gets longer in terms of wavelength, that angle with respect to the axis of that main lobe changes. And it goes from 54 degrees down to, at 10 wavelengths, it's only 16 degrees off the axis of the wire. But it'll also develop around 7.5 dB gain over a dipole, which is a 4-element Yagi anyway, which is pretty significant. We'll go back to this. Keep this in mind. That's a hint, the 10 wavelength thing. So this is basically how the Vee Beam works, is we put two long wires together and we put them at an apex angle here. You see how the radiation patterns line up. So we pick an angle so that the east and west major lobes coincide and they line up. And when you line them up like that, they complement each other and it increases the gain in that direction. So just like if you stack antennas, just the act of doing that, if you do it at the right distance, anytime you add two antennas instead of one, you're going to get 6 dB of gain over a single antenna. Of course, if you're splitting the power between the two antennas, you lose 3 dB of that. So the net is a 3 dB increase over what you get off of one wire, okay? So what we do is enhance the gain of the major lobes by picking an angle that lines those up so that these are in the same direction. Of course, here you got this other stuff going on too, which might be a good thing at field day when you're trying to contact, stations all around the compass. Make sense? So what I did was I did a lot of, this was kind of a winter project. I spent a lot more time modeling than I ever thought I would, but modeling straight line wires is easy. As soon as you bend them, it gets a little more complex, thanks to limitations in the software. But I decided to model this example Vee Beam, something that you might, if you've got a fairly big backyard, don't want to spend a lot of money on an antenna, this is something you might want to consider. So I picked a leg length that's not too long, but these are 180 feet, which is about 2.5 waves on 20 meters. And I built it. Now, EZNEC, you can't just do one wire 180 feet long. When you try to analyze it, a window will pop up and say, this segment is too long, and I can't handle the calculations. So you have to break the wire up into the whole wire into little bitty segments. So in this case, I have 53 segments here that I had to.
How much wavelength can mini-neck handle?
Pardon?
Or how much of a wavelength can EZNEC handle in a segment? You're cutting those segments down to be less than a wavelength?
Actually, a good rule of thumb is that if you keep each segment less than a quarter wavelength, you're probably okay. Now, what will happen sometimes, if you do that, you analyze at 3.5 megahertz on 80 meters, it works fine. And then you go to 10 meters, and if it gets too confused, it'll say these are too long, and you might have to make them. So what you want to do is make your model work at your highest frequency of interest, and all the other ones will work fine. So now I'm gonna pull out of this presentation just for a minute and show you what some of this looks like. So here's EZNEC, and what I'm going to do here is I hit open. You guys can see all this, right? Yeah. And I'm going to go to Vee Beam. Like I said, I did a few models here. The problem is every time you change the angle, you have to build a new model. I didn't think of all that when I picked this antenna. But, so here we are. And one thing you can do in here is view the antenna and make sure it looks right. And, I can do things like zoom it in. I can move it around, make sure everything lines up, and all that kind of thing. So whenever you build, you want to take a look at it and make sure it turns out the way you wanted it to. And if you don't, it won't take long to tell because you have lines going off in all different directions. And, you have to define a source here, and you tell it which wire the source is in and what percentage it is from one end to the other of the wire. It's pretty simple.
What wire size
Yep, you can put the wire size in there. That's in the wire program here. So if you notice here, I don't have my reader. So yeah, I got number 12 wire I used here on this row here. Now this is my wire schedule for this antenna, and I can't fit it all on the screen. And I'll warn you now about EZNEC. It looks like a Excel spreadsheet, but it's not. So when you're doing, like when I'm calculating this, I have to figure out, you can't apply a formula to a cell and have it carry through all the cells. So for a given triangle, I have to calculate, Pythagorean's theorem. So I have to calculate what's the delta X, the delta Y of each segment, and plug them in here and manually load each cell, which is a pain in the butt. But the nice thing is, on a symmetrical antenna, I build one side of the V, and then the other side, I just recopy the numbers and then put a minus sign instead of a plus sign. There are a few things you can do with EZNEC that are easy. Like if I want to change the height of the antenna above ground, you notice my Z-axis is all 40s here. And so there is a function here where I can change height. If I want to add 10 feet, I'll just put change height by 10 feet, and poof, they're all 50. So, so that you can do that, stuff like that. The other thing, and I'm not going to do it here because I don't want to scale it, but the other thing you can do is when you set the frequency of operation here, right now this is on what, 28? If I change the frequency and I hit rescale, I check that box right here, then it'll automatically adjust all the lengths and distances to that new frequency. So if I have a 10 meter dipole in my model, I want to see what it looks like on 20, I just put 14 megahertz in there and set rescale, and it changes everything. So it's the same antenna on a different frequency. So there's some things you can do very quickly, but building a wire schedule is not one of them. So anyway.
Free software still?
What's that?
Free software?
This is free software. This was developed, there was a time you had to pay for it. The developments, a fellow, the W7EL developed this over a period of about 15 years. And he's retired now, and so he just made it available for free. It's no longer supported, and I have information at the end of the presentation about where you can find it and how to download it. There's also a tutorial on YouTube you can look at that teaches you a little bit how to use it. So I'm not going to spend too much time going through design work here at all. That would be pretty boring. But so if I want to put this thing on, let's say 15 meters, 21 megahertz. I hit OK. And I want to see what this thing looks like in terms of gain. That's an azimuth plot. But if I change the plot type to elevation, I hit OK. And I hit plot here. And this gives me the the elevation plot for this antenna at this frequency. And I know the peak gain here is 14 dBi, and I see that it's 11 degrees. And that's important because when I plot the azimuth, when I want to do comparisons, I want to make sure I'm comparing apples for apples. And so when I do the azimuth plot, I set the elevation angle at 11. So that I'm looking at I'm plotting the azimuth based on the peak gain of the pattern. So I set that at 11. Then I hit far field plot there, and I get that at 15 meters. And I know I did it right because my gain is 14.08, just like it was on my other plot. So I'm plotting it right at the peak. Yes, Jesse?
When you're using that, and you're using it to design an antenna there, can you also use it to analyze an antenna that's already in place to see what you have?
Yes. You say in place in the program or in?
No, in other words, I have an antenna outside that I want to see
Sure.
what it's like, so I can use this for
Yeah.
design as well as analysis of
Correct.
an antenna that's already in place.
That's correct. Now you have to build your current antenna in the model, right?
Okay.
So if you have a dipole, 40-meter dipole up, you have to build it with the parameters you set in this program.
All the elements of the existing you plug in.
Yeah.
Okay.
So anyway, that's kind of and that's part of this presentation is about how you can use this software to play games and learn things on it. There's other settings you can set in terms of, if there's any loads or transformers in here. You can set the ground type. Is it real ground, artificial ground? Do you want your plots to be free space plots or over ground? You can do all that. So anyway. But we're going to...
An antenna on the side of the tower, can it compensate for the reflection of the tower?
I'm sorry, say that again, please.
An antenna on the side of the tower,
Mm-hmm.
can it create a pattern that reflects?
There is a way to model metallic objects in the proximity of the antenna. So you just have to figure, and I've seen that done. That's kind of above my pay grade right now, but I know it can be done. And I think in the tutorial on YouTube, they talk about how to do that. And that's interesting when you have multiple antennas in your yard, say, because you can do this all day, put it up, and then you get on the air and you say, this is way different than I expected. But you forgot to figure in the other antenna you have 30 feet away that may be impacting the patterns on other frequencies. So it's good to do that as well. Try to make it as realistic as possible.
Do you see a lot of change with changing wire size?
Yeah, actually, I've played with that, and when you change from like number 12 to number 14 wire, you lose about 1/10 of a dB a gain. It's just the resistance is higher, and it's not enough to get excited about, but you can also model tubing in here and tapered elements and all that sort of thing, and it calculates all that for you. That's a lot of the detail there's 70,000 lines of code in this thing, so it's fairly complex. And the NBS, National Bureau of Standards, they did some work on designing Yagi's, reference Yagi designs, 3-element Yagis, which are loaded in the library of files in EZNEC, and they come out very, very close. Yeah, so it's pretty accurate. How am I doing here? Okay, so let's go back to okay, so I was talking about this thing, and so again, we have 180-foot legs. I picked a 60-degree apex angle for a couple of reasons. If we go back to here, I said I had a 2.5 wavelength wire on 20 meters. So if I look at here, the main lobe center line is 30, sorry. sorry about that. I have hearing aids, and this thing talks to the hearing aid. It's a long story. Anyway, I should have shut it off. But, so at 2.5 waves, I have a 33-degree angle here, and it'll give me a single wire gain of about 1.8 dB. So if I added 2 of them together, it should be around 4.8, theoretically. Now I'm a little off. I'm not quite at 66 degrees, but there's a game you play depending on if you have certain bands that you're more interested in getting max performance. You can play with these angles and optimize it for certain ones. I'm trying to come up with a good average that works across the spectrum. So I picked 60, and you'll see in a little bit why another reason I picked 60 that has nothing to do with this. But so anyway, so this antenna is 60 degrees. Of course, this makes what? Equilateral triangle. It's a little easier to figure out.
What if you were to use an arc like this instead of straight lines? If you made it like an arc like this.
That's a great question. You could model that. You'd be there all day. Well, many days, actually. I don't know about that. It's an intriguing question. So you're saying if I went out a narrow angle for this long, maybe at my higher frequencies, and then turned it out a little wider for my lower frequencies.
Right.
So
Make like a spline curve or something.
it may work great. And you may end up with a mismatch where you get 3 dB across the whole spectrum. I don't know. But it's a good question.
The other challenge would be how you support your wire to do
Yeah, I
that.
was trying
Well,
to
yeah,
think of how to
infinite
go.
support.
Well, that's 2 more supports, because you'd have to go 1, 2, 3, and then 4, 5, right? So, done.
Did you make it into a delta, that you have it out there?
Yeah, there's a whole, that's next year.
That's the next one.
So I'm a fan of delta loops, and yeah.
So I'm just curious what happens.
There's actually reference design in EZNEC about delta loops. So, yeah, absolutely. Then everything changes again. So this is another eye chart, but essentially, if I looked at that V that I designed and compared it to a dipole at the same height, what I did here is plot across all the bands from 1.8 to 30 megahertz what the dipole pattern yielded in terms of dB. This is dBi is dB related to isotropic, right? So a dipole is 2.1 dB better than isotropic. So, and then here's the Vee Beam. These are easy to compare, and then I do the math manually and figure out what the difference is between the dipole and the Vee Beam, okay? And there's a couple of things I'll point out here. My light sensor is, oh, there we go. So basically, because this is only 40 feet high, at the low end of the spectrum on 160 and 80, like any antenna so low to the ground, most of the radiation is up. And it acts more omnidirectional, no matter how you shape it. So there isn't much gain there. In fact, the Vee Beam is down on gain on 160 compared to a dipole by 1.7 dB. It's about equal to a dipole on 80, but then starting from there, things get a little better. So I got about almost 2 dB of gain on 40 and 30, but at 20 meters, now I'm up to 4, and then from 17 up to 10 meters, you can see they're all in the, except for 12, I don't know why, but they're all around 5.5 dB gain over a dipole, which is better than you'll get out of any tri-band, at least a short tri-bander. So you start to get some pretty good gain. This particular number on 80, I put an asterisk here because even though the gain is not that great, the radiation angle is lower, so it's more useful in terms of covering longer distance contacts. So on 80, I measured the V's gain at 50 degrees above the horizon versus straight up. I have plots, and I'll show you these. But. So let's take a look at what these do a little bit. So on these plots, what I've done is, these take up a lot of space on the slide. So I've kind of chopped these up a little bit. So the elevation plots, on EZNEC, you can print the plot, or you can just the plot plus the data. So I did the plot plus data on the azimuth and just the plot on the elevation. Okay, and you can play around with these and all that. This line width, I made them thick because I wanted to make sure you all could see these in the back. I think you can. But when you're working on it, usually the medium or narrow line width is a little easier to read. So, but it'll give you all your interesting statistics here, or you might not find them interesting, but it's there. So on 80, you can see actually the V, and this V is oriented east and west. So this actually favors north and south by about 3 dB, so on 80 meters. But you can see, here's the dipole in blue. Our trace, what we care about, is in red. And you can see that the dipole's a little stronger, but it's stronger in the straight up direction, which is a good thing if you're just trying to talk to someone close by, 100, 200, 300 miles away. But if you want to reach out to the coast, then having a 50 degree angle here is actually better. So this is really no worse at distance. It's just a little weaker when you're communicating close in. So, and then when you get to 40 and above, then things start to get a little more interesting. So now on 40, we have a little bit of gain, not only in the forward direction at 90 degrees, but also at 45 and 135. So we're getting a little bit of useful gain over a broader range than the dipole. And you can see, again, I keep pointing to the fact the elevation angles start to work their way down more quickly with the V. So I'm not going to go through every one of these in detail. When we get to 20 meters above, things start to get more interesting. I mentioned earlier that one of the drawbacks of the V is that the major lobe is fairly narrow. And you can see that here. So it's stronger than the dipole, but only through a fairly narrow range of azimuth. That maybe is a downside, but if you look 90 degrees off the sides, this thing is 7 or 8 dB better than the dipole would be at that height. And you get a little bit of gain off the back too. And as you can imagine, as we go up in frequency, the gain gets higher, the patterns get more complex. So at 15, it beats the dipole pretty much in every direction, totally. So, pretty good field day antenna because, you're stronger almost all directions around the compass. And you can see where that energy is coming from in the elevation plot. Compared to the dipole, it's redirecting this upward energy out horizontally where it can do you more good. Here's 10 meters. Now on 10 meters, you notice there's 2 peaks there. Anyone know why that's the case? Remember I said it's a 60-degree angle of the wires. So if we get up, so a 180-foot wire is basically 5 wavelengths at 10 meters, right? So it's 36. So at 5 wavelengths, that angle of the major lobe compared to the axis is quite a bit small. It's down around 22 degrees. So at 60 degrees, our wires are not optimized for 10. They're too wide. So instead of getting 1 strong forward lobe, I'm getting 2 not quite as strong lobes that are separated by around 24 degrees. So it's not that angle doesn't optimize it for 10. Now, in some respects, you may say it's better to have 2 peaks than 1. So, but it's just a character. You can just see how it changes over frequency. So here I didn't plot. Here I just called out this is right off the M² website, and this is the forward gain compared to a dipole of the KT34. And the Vee Beam I described is a little bit about 0.4 of a dB weaker on 20, but it's almost a dB stronger on 15 and about 0.5 dB stronger than 10. So that Vee Beam, if you could stretch out 280-foot wires, 40 feet off the ground, essentially equivalent to a KT34XA in that major lobe. Now, the next thing I do here is compare it to the Yagi in terms of the azimuth pattern. And this highlights what makes them different. The V isn't a better antenna than a Yagi. It's a different antenna. And you just want to understand the differences. So here we are on this is a two-element monoband Yagi, which is pretty much equivalent to a 3-element tribander, because the tribander's inefficient, on any one frequency compared to a monobander. But it gives you an idea what happens here. So on 20, we get a little bit more gain at 90 degrees, but we also have these dips, about 30 degrees off center, where a Yagi has a better pattern as far as filling in the general direction you want to go. All right, so I'm not saying this is better than Yagis. I'm just saying it's different. You get the gain in certain directions, but this overlays that Yagi on the Vee Beam, and you can see the difference in the pattern. I didn't do all the bands, but I did it at 15 and 10 meters. You see at 15, it's not such a big deal, and at 10 meters, it's basically not a big deal at all. So if I got a 2-element monobander and a Vee Beam, I'm going to have 2 peaks here that are stronger than the Yagi, but I also have all this other stuff going on in the northwest and the southwest. That's something to keep in mind when you want omnidirectional coverage, right? Like in a field day or emergency situation. I did the same thing with 3-element Yagis, but we'll kind of skip. It's the same idea. So now I'll talk about a couple of deployment, practical deployment options maybe. You need a big yard. I said that up front. So here's a Vee Beam pointed north, and it's 180, this is what I modeled, 180 foot legs, 60-degree angle, 40 feet off the ground. And when you look at the map of the world from centered on this location here, you'll see where's the DX, right? So over here I've got China and India and all those stations to the north, and also long past the south. So you really want kind of a north-south orientation to your patterns. With the Vee Beam, you get this stuff going on the sides here too, which is helpful into Africa and also to Southeast Asia and Australia. So, and you even get a little bit of a pip here to the southeast, which gives you good coverage of South America. See? So if you can only put one Vee Beam up and you want to work some DX, my suggestion is aim it north, and you'll get pretty good around the world coverage. The other thing I mentioned too is with EZNEC, everything's very precise on these patterns, but in the real world, they tend to fill in a little bit, is generally the observation you hear. I've observed that and others too. So ground reflections from power lines or whatever in the area can kind of muddle these things a little bit. So maybe your gain isn't quite as high, but these peaks and valleys usually are filled in somewhat. They're not as precise and accurate as that in the real world. So this is out of the ARRL antenna book, or at least this concept. So here's an idea. If you've got the room, this is, you might say, well, one Vee Beam is good. I'd really rather have 2. But this is the way you can build 2 Vee Beams and end up with a bunch of antennas. So here, my original Vee Beam is here, and now if I've got 360 feet of space, I put this straight out. So this is east, west, northwest, and northeast. This relay switch box, what it does, I'm not getting into the details here, but there's designs for that. So it helps you to select 2 of the 4 wires, in different combinations. So this is something you would build into a weatherproof box, put it on your pole or mast up near the feed point, and then use, balanced feed line to your station. So when you do this, we'll look at it from the bird's eye view. In this example, the relays select the northeast and northwest wires. So you get that north-south pattern that I was talking about before. But then you switch the relay, and now we pick the northeast and the east wire, and we get that northeast-southwest pattern. And we switch it again to the west and the northwest wire, and we get it northwest and southeast radiation pattern. Okay? So there's 6 different directions I've covered with my Vee Beam. And then the last thing I can do is select the east and the west wire. Now I have a 360-foot long doublet, which, by the way, is an extended double. It's 2 5/8 waves in phase on 80 meters. It provides 3 dB of gain. So for 160 and 80, where the Veeam wasn't particularly efficient, you could use this configuration for north-south patterns on 160 and 80. So again, you can just kind of steer this thing around with a switch, right? That's kind of cool. So with 4 wires, you get 4 unique antennas, and that doublet, by the way, you can use that on any band. If you loaded that on 10 meters, you'd get about, well, at 10 wavelengths, it's about 7+ dB of gain, roughly equivalent to a 4-element Yagi, monoband Yagi. So that's kind of the end of my portion on the general idea on Vee beams. So I wanted to see if there's any questions on that. This is kind of more of a permanent or a home type installation. Obviously, you need a pretty good yard, to get the wires out there. But yes.
Did you look at sloping V where the bottom of the 2 legs are at the ground?
I didn't model it yet, because now I have to add that Z component changing with every wire segment. But from what I've read, it's very common if you don't have 2 trees or 3 equal height masts. A lot of people slope the low ends of it, and it doesn't really affect it. The elevation angles come up a little bit because it's lower to the ground on average, but it makes very little difference. I mean, you don't want it 3 feet off the ground, but if you've got, as long as you've got it 20 feet in the air.
The one I had in Antarctica was a sloping V, and we brought it all the way to the ground.
Oh, you did?
Terminate lines going back.
Okay.
For the.
So if
but
you
it
had
was
it
also-
terminated, that was made for unidirectional transmission.
Right,
Yeah.
but it was also a much bigger antenna too.
Yeah.
It was on a 110-foot tower, and the legs were over 350 feet, so.
Yep.
What frequencies were you using, and what kind of, do you use coax to feed that, or ladder?
So we had, I don't know, 1,000 foot of 7/8 hard line that ran from the building out to the base of the tower. And then we had and all this was designed by the Navy decades ago, had the transformer, because they were set up for doing like 5,000 watt transmitters.
What
I only ran,
frequency?
I think, 1,000-watt transmitters. But we had the balun at the base of the tower, and then a balanced feed line, home-built balanced feed line that was probably 8 inches across, 9 inches across, that ran up the tower to the legs, and then came back down into the terminating resistors, and there was a ground laid out underneath them.
Cool.
And this is how, like my antenna, is how I typically would do. I take the balance feed line as close to the house as I can. It makes sense, but outside the house, I'll put a 4-to-1 balun there and use a short run of coax to the tuner into the rig. Now the SWR can be high on that coax, so you want to use big stuff and a shortest length if you can, but it's more practical than trying to run the balance feed all the way into the back of your tuner,
I just use, I drop it down off my tower, it's only 32 feet down.
By dropping down 40 and a 75 meter inverted V, essentially is what it is. Then you get perfect impedance and you don't need a tuner.
Yes. Well, the impedance-wise.
I'd like to see the pattern.
Impedance, well, a dipole in free space horizontal has about a 70 ohm characteristic impedance. When you drop it into an inverted V, then that lowers and you find that 50 ohm, so it's a perfect match. Now, the radiation patterns aren't as strong, and that's something I have in my another presentation where when you drop it down, it's a little weaker of a radiation pattern too. But in this case, what's nice about it is you use the balanced feed and a tuner, so you don't worry about, I mean, EZNEC will calculate impedances. I don't care. I'll just tune the knobs until it's tuned, and so I'm done. So that's the Vee Beam in general, something you could put in your big backyard maybe. Now I also played around, what do I do for field day? I don't really want to put up Yagis anymore at field day, So is there something we can do here? So what I did here was model a shorter one with just 90-foot legs. So it's about almost a wave and a half. A wave and a half on 20 meters is 105 feet. I was trying to keep it under 100 feet long. And cutting it down to 90 feet had really no appreciable impact on the gain. So I made 90-foot legs, and I used a height of only 25 feet here, And I plotted here again the dipole, and the thing is here with such short legs, what's the right angle, right, to optimize the performance across at least the higher bands, 20, 15, and 10. So I modeled 60 through 100 degrees angle and plotted the results compared to a dipole. So basically, the 70-degree angle gave me, you know, the best option here in terms of performance. So I modeled that. The other thing I had to look at is what's the best height for this thing, because height affects your radiation pattern too, right? So I modeled it at 25, 30, and 35 feet high, which is about all you're going to do in the field, and found that the 30-foot high, that's a good target height to get. And at that point, I get almost basically 2 dB of gain on 20, which isn't a lot. But on 15 and 10, it's equal to or better than the tri-bander. 4.2 and 5.6 dBd gain. That's pretty good. So I modeled this thing, again, 90-foot legs, 70-degree angle, and again, just plotted that. This is just how the model looks in EZNEC. I don't know if you can see that purple line on here, but that's the current distribution across the antenna. So they will plot that as well when you do the analysis. So I can see that I'm at, not quite at a current peak here, it starts to dip a little, but I'm at my feed points at a high current point, which is generally good, you know, most efficient. So anyway, and then again, more plots, sorry. You get a little crazy with this stuff. So again, the red lines are V and the blue lines the dipole. So you can see here that on 20 meters, I have a little gain east, but again, I'm losing a little bit northeast and southeast. So yeah, that's not so good. But so it's okay on 20, it's not great. You can see the elevation over there is better though than the dipole, right? So maybe I'm single hop to the East Coast instead of double hop. There's 3 dB there. All right, 15 starts to look better. And on 10 meters, it's quite a bit better. So we're getting equivalent of gain of about a 3-element monoband Yagi at this point, just on the little front and back part. But we also have good lobes, northeast, northwest, southeast, and southwest. There's people up there to work as well, right? And you can see the difference in the elevation plot is quite significant. And at 40 meters, again, like the other earlier model, it favors north and south, which isn't ideal for field day, but you're talking a couple of dB. And you see the elevation plot. The V isn't as efficient, but all the extra gain out of a dipole is straight up in the air, so who cares really? And 80 meters, it's pretty much a dipole on 80. It's so low to the ground, it doesn't matter what you do to it. So the Vee Beam might be a good option for field day. But I got thinking, it'd be nice to have some extra oomph going eastbound, you know, for field day, get a little more gain out of there. We could go back to the 180-foot model or even a 360. There's a DJ, a guy in Germany, who's published one of the ARRL books years ago. He ran 512-foot legs on his Vee Beam. It had some pretty amazing results. But when you do that, the gain on 10 and 15 isn't a lot better unless you close the angle down. Then you start messing everything else up. So to have a cross the spectrum type of antenna, I figured, you know, maybe there was other options available. And obviously 180 feet legs, that's tough to do at field day, hold all that up. In fact, if you're only 30 feet high and 180 feet apart, I'm not sure that the number 12 wouldn't be touching the ground in the middle. So you might need a lot more than 3 supports. So then I said, well, what if I threw a Yagi type reflector behind the V? Now, this is kind of a pie in the sky thing, right? And I'll admit up front, it didn't turn out as good as I had hoped, but I know why. So what I did is I built a model with this 20, just for 20 meters. 10, 10 and 15 are good. But I put a 20-meter reflector behind the V just to see what would happen. Well, what happened is I got about 0.8 dB gain. It's not very much. In a Yagi, the dipole and the parasitic elements are closely coupled. So one induces current, RF current on the other. They play back and forth out of phase with one another. The coupling between that V and that reflector isn't nearly as tight. So it didn't have the impact. I was hoping to get 2 to 3 dB, but I didn't get that. But I got 0.8. So, but that brings our 20-meter gain up to almost 3 dB. Not bad. But it cost me 38 feet of wire. That's pretty cheap dBs, right? So that's not bad. But then I took it a step further and said, well, what if I put some directors on there, right? Now, I won't show you the table. The wire table for this is a little bit ridiculous, but it's about this long. So I put 1, 2, and 3 directors. I modeled all of those to see what that would add. And so this is 1 director, 2 directors. You can see on 20 meters, I get up to 3.1 dBd gain, 3.7 with 2 directors. So I'm still seeing that limited coupling between the V and the parasitic elements. But the 2 directors together add another dB of gain on 20. So I got 0.8 with a reflector and another dB on the front end. So the 3rd director didn't help much. It doesn't affect 40 and 80 meters, so I can still use 1 antenna on all the bands. But now,
Did you change the length of your reflectors and directors?
oh yeah, I optimize all those, 1/10 at a time. So now I got 63 feet more wire, and I end up with almost 4 dB on 20, and 3.8 on 15, and 5.5 on 10 meters. So comparing that again to the Yagi, I'm about 0.8 of a dB below the Yagi on 20. And I lose about a dB on 15, and I'm about the same on 10 meters. So, for 180 feet of wire, that's pretty good, I think. It's a lot easier to put up. So I called this thing the YAGV, for lack of a better term, YAGV. So this thing now is giving me that almost 4 dB gain to the east. Again, on 20, I still have those weak spots at northeast and southeast. But I'm pretty good to the west, so I can work a lot of Californians. But on 15, things look better, and my lobes to the northeast and southeast are stronger now. And on 10 meters, it looks a lot better, I think. So it's pretty much stronger than the dipole in all directions. And I've got basically the equivalent of a 3-element Yagi to the east and west. One thing about these directors, if I have these V wires going out like that, I can put some places to physically attach the directors so they fit inside the span. So I can support them with the same wires. All I have to do is clip them onto the wire before I raise it. And you'll see the V with the directors in the middle. So the antenna is no longer, not any longer or anything like that. And here, just to make sure I was on solid ground, I got rid of the reflector and just put, if I just don't want to put all that stuff up in the air, I could just put the V up with the 2 directors in the middle, and that's the result I get. So I'm about 3 dB gain on 20 meters, 4 on 15, and 5.5 on 10 meters. So again, because the spacing, that director, the reflector ended up being 22 feet behind the V. So the whole mess is longer. And then you have to support the ends of the reflector too. So that's 2 more supports you need. Now they can droop, but they have to be kind of up. in the air to be effective.
Would you tie them off to the main legs for support?
You mean these directors?
Yeah.
Yeah, what I'm gonna do here is I'll put like an insulator in line here and just use pieces of string to hold that up. And so when you pull this leg up, these legs up, those directors will come right up with it. I'll probably use like number 16 wire in there so it's lighter. So just some construction notes on building this thing. I think the main legs of the V probably should be numbered 12, especially if it's windy. But the parasitic elements, you can just put quick disconnects on there. So you just snap them on, to the main wire, pull it up in the air. How do you hold 70 degrees? I pondered about that a minute. I don't want to be out there with a protractor, So I'm just going to get some light. I won't call it fishing line, but I have some really thin line I get from KF7P that supposedly has a 200-pound breaking strength. So I'll put a piece of string between the end insulators, and so when we tie off the ends, we'll make that taut, and that'll hold our 70-degree angle. And then again, the center support can be tower. I want to get a little higher than 20 feet, but I have a mast. I'm waiting to hear back on some replacement tubing, but if we can get the center of this thing 30 feet in the air, or maybe even 35, and then slope the ends down, that'll be sufficient. So, but it doesn't have to be tower necessarily. It can be a push-up mast. And then on the end supports, there's a way to just splice in you could use a 16-foot 2x4, or get even higher by splicing two, together like this. Just bolt them together with wing nuts, stand them up, guy them off, and you can get that up in the air. Hopefully there's sites where there's trees and you just throw a line over a tree. But if there's no trees, you'll have to support that. That's not easy to find around here, I'm discovering. I talked about the Aggie reflector, and again, the feed line, you just want to make sure it's not a resonant length. And I have a chart I can share. These are distance or lengths to avoid. So just to summarize, my YAG-V and Vee Beam, it's a lot of gain for the dollar, compared to a $3,400 tri-bander. It's easy to erect by one person could do it, but a lot easier with two. And it's one antenna for all the bands. You don't really need an extra low band antenna. So that's great for field day. It could be bi-directional. You have the multiple side lobes, so you get more coverage around the country. And you need some space to get good gain, no doubt about it. So for basic portable operation or emergency communications, the small basic V with 90-foot legs, I think, is a realistic option. Plays better than a dipole, a lot better at the higher bands. And if you're more competitive or you need extra strength to the east or some direction, like for field day, maybe the YAG-V with the directors and even the reflector, if you have time to put it up, is a better option. So this is just some information on that software, and I can get into that more if you want, but basically it's available for free download, and then there's that YouTube video that kind of goes through how to do things. And do things like, I didn't show you how to do it, I could, but you can create an antenna, have a plot, and then you can add a trace. So you can go back to your file, other traces you've saved, and overlay them like I showed you here, the red and the blue. So, just want to caution you here. I've not built or used any of these antennas yet, so this is all theoretical, and no guarantees, right? But I've found in general over the years that if it works in EZNEC, it usually plays pretty well in the real world. So, but again, no guarantees. So my plan right now is to build this YAG-V thing and maybe use it this summer at field day. And I think depending on how many people are available to put it up, I may put the whole thing up. Maybe I'll leave the reflector off. I don't know. That'll be a game time decision, but I'm gonna give it a try and see how it works. And, but if any of you think it's a good option for you, if you're interested in deploying one at home or some location other than that, let me know, and I can walk you through the modeling. We can build a model to your specs, something you can fit in your yard, and help you out with figuring out the details of that. Okay? And that's it. Thank you.
One comment, just something to consider when you're thinking about this, especially for field day where there's a lot of traffic. The thing you can do